Welcome to the first test review for Chemistry 1406. If this is something that you guys like and would like me to continue to do on a regular basis, please feel free to let me know. Just let me know maybe like a week or at least a few days prior to the exam, and I am happy to hook you guys up with a test review for every test. Just let me know. All right, let's get into this. Yes, Ali?
Just a quick question. Are these test reviews kind of universal across all the professors for their tests, do you think?
Yes. For Chemistry 1406, we have a standardized textbook across all campuses, and so they're teaching effectively the same topics. There will be a little bit of variation between professor, but this is why, even though I use a practice test that I'm providing, students can feel free to bring questions from their professor or from on any topic that they might be covering in their upcoming test. And that's to try to kind of allow for some of the differences. But for the most part, the tests are going to be covering roughly about the same stuff.
Oh, okay. Well, thank you, sir.
Yeah, no problem. All right. Oh, thank you. All right, so let's go ahead and jump into this. Do you want to kind of jump around? Does anybody have a question that they, either from the practice test or otherwise, that you want to kind of go over? Or is there, or should we just kind of like go through it sequentially, 1, 2, 3, 4? What do you think? Okay, let's do it. All right, so the first thing is scientific notation. Write point 000000033 in scientific notation. When you're writing in scientific notation, what you want to do is you want to move the decimal point in such a way that the final number ends up being somewhere, or basically a value in between 1 and 10, basically less than 10, but greater than or equal to 1. Okay, so here's what we're going to do here. I'm going to take my little squiggle writer, and actually I'll just use this one. Here we go. And first I look for where I want to put the decimal so that the number will be less than 10 but greater than 1. In this case, I'm going to want to put it between the two threes, right? That would give me 3.3. So if I put it one further, there'd be 33, which is greater than 10. But if I put it one before, it would be 0.33, which is less than 10. So I have to put it right there between the two threes. Okay, good deal. Now, I'm going to shift the decimal point over as many times as it takes until get to where it is that position. Then I count how many places I shift it. 1, 2, 3, 4, 5, 6, 7. And absolutely, Linda, you nailed it. It's 7 spaces, so it's going to be 3.3 times 10 to the negative 7. Now, essentially, sometimes students I notice get confused when with scientific notation. They're like, well, do I shift to the right or do I shift to the left? I mean, if it's a positive 8, do I shift to the right, or if it's a negative 8, do I shift to the left? And the problem with that is that left and right, if you're going into scientific notation, you'll shift it one way. If you're going out of scientific notation, you'll shift the other way. So the left and right thing isn't super helpful. The easiest way that I've come up with for describing this with scientific notation is this. Essentially, you can just think of it as if the number is greater than 1, the exponent in scientific notation should be positive. If the number is less than 1, it'll be negative. The exponent is negative. And that's the easiest way I've found to do it. Like, if it's a 3.3 times 10 to the negative 8, let's say for example, I had a number, and I'm just going to make up an example here. Let's say, for example, I had a number that was like 3.4 times 10 to the 5th. if I want to figure out, okay, well, how do I write this in normal notation? I know that because this is a positive exponent, I'm going to want to shift this in such a way that allows me to get a number greater than 1. Well, I can't shift this way because then that will be less than 1. I have to shift it the other way. So I realize that this is just going to be a 3.4, but then I'm going to have to shift it to make it greater than 1, so I'm going to have to shift it to this direction 5 times. 1, 2, 3, 4, 5, and then I just fill in the zeros. 1, 2, 3, 4, and here's where the new decimal place would be. Of course, the number of sig figs you start with scientific notation is the number of sig figs you end with. So when I actually write this number, I'm not going to write it as 34 or 340,000 with a decimal point, because that decimal point will cause those zeros to be significant. The decimal point that I originally put there is just for the purposes of tracking. So I'll take that decimal point off at the end, and that will give me the number that I would use, because that would be two significant figures, the 340,000. Does that make sense? Any questions on that? Okay. I'm assuming we're good. All right. Now let's go ahead and take a look at the next question. It says, which of the following numbers contains the designated correct number of significant figures? And you're saying A, and that's absolutely correct. If I was to, and feel free to turn on your mics and respond. That's totally cool. I love an active session, and I like hearing your voices. That's no problem with me. But yes, you're absolutely right. This is going to be A. That'll be 3 significant figures. How many significant figures is B?
It's actually 3 because the 0 is between the 1 and the 4.
What about C? How many sig figs is that?
5.
5. Trailing zeros are significant if there is a decimal point. What about D? What about D?
D is just 4.
It's 4.
Yeah, D is just 4. D as in dog is 4. And a lot of students sometimes will make the mistake of including these first 2 zeros as significant. They're not. Leading zeros are never significant. So yeah, that is going to be only 4 sig figs. And then the last one should be how many?
3.
3. Very good, very good. Okay, now number 3, it says, which of the answers for the following conversions contains the correct number of significant figures? So if we're looking at this, so Linda is saying D. If we're looking at this, D is in fact not correct. What you got to look at here is, first of all, the original number, how many sig figs is that? And you also have to look for whether or not the conversion factors are exact or whether or not these are estimated conversions. So 1 pound is equal to 2.20 kilograms. This conversion factor is an estimated conversion because there are very few exact conversions between metric and English. In fact, there's only one. The only exact conversion between metric and English is this one down here. 2.54 centimeters is equal to 1 inch. It's the only exact conversion between English and metric. Every other English to metric conversion is going to be an estimated value. Yes.
Yeah. Are you saying that that in trying to answer this question, you also have to take cognizance of the way the conversion factor is set up, or you're just looking, because I was just looking at only the answer. I didn't look at how it is set up. So are you supposed to take that into cognizance while you're trying to answer that question?
Well, okay, so all of these are set up correctly in that sense. But what you have to be careful of is, do you have to consider the significant figures of the conversion factor or not? See, a conversion factor will always have one reference value, but it may or may not have a limited number of shall we say, it may or may not have a limited number of significant figures. Okay, so I'm gonna take the ones that are okay. So definitional values have unlimited significant figures. So for example, the ones I'm highlighting in yellow here, the 1 hour, 60 minutes, that is a definitional value. 1 hour, 60 minutes, a definitional value. By definition, 1 hour is equal to 60 minutes. So that has unlimited significant figures. The significant figures are not limited by that. Likewise, 12 inches is equal to 1 foot. That is by definition. And the 2.54 centimeters is equal to 1 inch. That is actually also an exact conversion. So each of those has unlimited significant figures. However, the ones that I'm going to mark in kind of a dark blue purple, these are not exact. They're metric to English that are not exact, and therefore these have a limited number of significant figures. Now the 1 pound, that 1 is a reference value, and reference values have unlimited sig figs, but the 2.20, that is a measured comparison. And measured comparisons do have limited significant figures. So the rule for multiplication and division is what? What's the rule for multiplication and division?
You look at the total, the lowest of all the total numbers or the values.
Yeah, whichever. Yeah, your
That's
answer
at least
cannot have
six
more.
is correct.
Yeah, your answer has to have the same number of sig figs as whichever numbered value has the fewest significant figures. Exactly,
Yeah,
Heather.
that's true. So
You
it should
got
be
it.
that should be
Yeah, you got it. So in this case for A, 24.0 has 3 sig figs, 2.20 has 3 sig figs. So my answer should have 3. It should have 3, but it doesn't. So this is wrong. B, it has the 2.543 has 4 significant figures,
Yes, I see.
and the 39.4 is a measured one, so that only has 3 significant figures. So my answer once again should have 3, but clearly this has like 7, so that's wrong.
Mm-hmm.
Then we look at the next one. 24.95 has 4, but since this is a definitional value, it has unlimited significant figures, and my answer should also have 4. In this case, it does have 4, so
That's
this
correct.
is your correct answer, C.
Mm-hmm.
For D, it's 12 feet. That's 3 significant figures, 12.0. This is a definition. This is a definition. But the 370 here only has 2 significant figures. It should have 3. It doesn't, so this is wrong. And then the last one, it starts with 1 significant figure, and while there's 3 sig figs in the conversion factor, and that's an estimated value, this should only have 1 significant figure, and so that's wrong as well. Does that make sense?
It does a lot.
Yeah, the tricky thing you gotta watch for, is those the conversion factors, because sometimes they're exact and sometimes they're not. Basically, the rule is if it is a definition, like 12 inches equals 1 foot, or a metric conversion, 100 centimeters equals 1 meter, then you have unlimited significant figures. However, if it's an English to metric conversion, oftentimes that's an estimated value, and therefore you have to take into account the significant figures there. All right, so let's skip over to number 4, shall we? And if you decide to want to skip at any point, move to a different one, just let me know. All right, so yes, Carissa?
Quick question. Hey, the first class you did, you put up a table of conversions.
Oh, yes, I did.
Can you by chance do that again sometime today?
Absolutely.
Okay.
I can, tell you what. What I'll do is I'll actually post. Let's see. Let me check and see if I have it. Oh, conversion factors. Table of conversions. Yep, I have it. All right, so
Right.
I'm going to go ahead and I'm going to add it to the Lucid Spark board. I'll also post the link in the chat. What
Awesome.
I'll
Thank
do
you.
is I'm gonna drag this over a little bit. I'll drag this over, and I'll just put it off to the side here, so that if you're in Lucid Spark, you can actually just drag the screen over and look at it. Just click on this little hand symbol, and this the go to the pan one, the little hand, and then you can click, hold, and drag it around. But I'll add image, um, desktop. Scroll down to table of conversions. Here we go. I'll switch back to select. It's really tiny right now, but I'm going to make it big. Yeah. So this is a useful table of conversions. It has English to metric, metric to English, and it also has the prefixes. So I'll just leave that up there on the board. And I'll also, and for those of you who are on Lucid Spark, if you want to practice doing some of these problems on your own, you can feel free to like write all over the board over here, away from the main page, and then kind of like check back with us and see what we're doing and see if you're getting it. That's totally cool. I think that's one of the fun parts about this. Also, if anybody decides like, hey, I think I know how to do this, I'd like to show how it's done, feel free to jump in. I'll let you teach the class, so to speak, on how to work out a particular problem. That's totally cool with me. All right. So now 9.31 is the same mass as what? So this is tricky. Um, what we're going to have to do here is we are going to have to convert this to each one of these units. Um, now, we can maybe rule out some of these possibilities to make this a little bit easier. Which unit is larger, a gram or a kilogram? Which represents a greater amount?
Kilogram.
Kilogram, yeah. So is 9.31 grams going to be equal to 931 kilograms?
No.
No. No, 931 kilograms is like the weight of a car. 9.31 grams is like the weight of a pencil. So that's definitely not going to be right. So some of these you may be able to just look at and be like, okay, that's definitely wrong. The rest of these, it's a little trickier. I mean, it's going to be a little bit harder to tell exactly, is this correct or is this not correct? I mean, I just don't know. So what we can do is we can set up some different conversion factors here. We'll start with the 9.31 grams. And what unit is going to have to go on the bottom here? Because we always put the units first. What unit is going to go on the bottom? Yeah, grams, right? And then let's go ahead and start by like maybe, I don't know, maybe let's convert to micrograms. What do you think? So how many, well, the unit we're converting to is going to go up here. I'll do microgram. Now, as a general rule, what I like to do is I always put a 1 in front of the prefix unit, and then I take the meaning of the prefix. So prefix is like the micro, and then the grams is like the base unit. So I put the meaning of the prefix in front of the base unit on bottom. So now if you look over at micro on our little conversion factor chart over here, micro here is 10 to the negative 6, or 0.000001. So that means 1 microgram is 10 to the negative 6, or 0.000001 grams. That's what I'll go ahead and write here. I'll use scientific notation because I'm lazy and I don't want to write 0.000001. So 1 microgram is equal to 10 to the negative 6 grams. I multiply the top, divide by the bottom. Of course, I don't really have to multiply by 1. But that's going to give me a really big number. It's going to give me 9,310,000. So that's definitely not going to be the correct answer, right? 9.31 grams is not 931 micrograms. It's 9 million micrograms. So that one is gone. I can then try this again using a similar method, and I can convert grams to centigrams. And I'll put a 1 in front of my prefix unit. Centi is prefix. And then what do I put in front of grams? What am I going to put in front of grams?
.01.
Yeah, 0.01 or 10 to the negative 2. Either is fine. I'll put 0.01. That's easy. 0.01, and so I divide by that. That gives me 931. Well, that's close, but no cigar. 931 centigrams is not 93.1, so that's not right. So let's look at the milligrams one. 9.31 gram. And grams is going to go on the bottom. In this case, milligrams is going to go on top. And I'll put a 1 in front of the prefix unit. And what goes in front of grams then?
1,000.
Not 1,000. Milli does
In
not
front of the
mean
gram, 1 gram.
Oh,
No,
you
what
could
am I
say,
saying?
okay, so you could say,
What am I saying?
if you wanted to, you could say 1 gram is equal to 1,000 milligrams. That's true. That's my personal preference is to go ahead and use the actual meaning of the prefix, which if you look at the milli, it actually means 10 to the negative third or 0.001. So in this case, I'm actually going to go ahead and use 0.001. But you could put 1,000 milligrams on top and 1 gram on bottom, and that would give you the same answer. It's going to be 9,310. Well, this is great because that is exactly what this is, 9,310. So it matches. So that is what 9.31 grams is equal to. Now, just as an FYI, one of the reasons why I usually prefer to use the prefix, the meaning of the prefixes, instead of like using like 1,000 milligrams, is because if you look at kilo over here, kilo also means 1,000. And a kilo means 1,000. So if you're using 1,000 for kilo and 1,000 for milligrams, it's easy to kind of flip those and make a mistake. But if you're consistent and you say, okay, well, the prefix is the prefix always gets a 1, and then I'm always using the meaning of the prefix in front of the base unit, that allows you a consistency that prevents you from getting confused and making mistakes. Does that make sense?
Yeah.
Okay, cool. All right. So let's go ahead and take a look at number 5. It says, which of the following setups would convert centimeters to feet? Linda says E. Absolutely. That is correct. So the key thing with conversion factors is to follow the units. If you follow the units, you're going to be safe. Whatever the unit is that you start with, that's the unit that typically has to cancel, so it has to go on the bottom. And so that cancels out. Then the unit you're looking for goes on top. Or if you can't convert to the unit you're looking for directly, you might have to convert to an intermediate unit. That unit then has to cancel out, so you put that one on the bottom. So this cancels out with this, and I'm left with feet. Note that centimeters cancels out here to inches, but then inches and feet don't match. See that? This doesn't match with this, so that doesn't work. Centimeters here. Oh, whoops, actually, This is wrong. E is wrong. Sorry. And the reason it's wrong is the units actually match, but the numbers are wrong. 2.54 centimeters is equal to 1 inch, not the other way around. Unfortunately, it's this conversion factor that's the problem. And that's an easy mistake to make. In fact, I actually didn't even notice it at first.
Oh,
You have to always make sure that the top value is equal to the bottom value. 1 inch is 2.54 centimeters, so that is a valid conversion. 12 inches is equal to 1 foot, so that's a valid conversion. And once again, the units are cancel out in the same way, but the numbers now actually match. And so this gives you feed
let's
as well.
see.
So both C and E have the correct unit position, but only C has the numbers in the right
Yeah.
place. And then of course this one doesn't match with this. This one doesn't match with this, so those can be ruled out. So here is our answer.
Wow.
Good job.
That's
Now for number 6, it says how many kilograms are there in 30.4 pounds? For this, this is just another conversion factor problem. We take the 30.4 pounds and we multiply times conversion factor. And it looks like people are saying B. That looks good. And that's exactly right. B is correct. Because pounds has to come on the bottom. And I have to convert to kilograms. And for that, I'm going to use the conversion factor that you can actually find over here in the English unit conversion. That the 1 kilogram is equal to 2.205 pounds, or 2.20 pounds if you're not wanting to use all those decimal places.
30.8. Oh, shit.
Now the key thing here is that this is 3 sig figs, this is, 3 sig figs, this is L, not a 1.
Yeah.
So your answer should have 3 sig figs, and that's why it's 13.8 and not 14. Although I will say this, if you had used 2.2 pounds, then the answer would have been E. And if you had not used this, if you had used 2.2 pounds, the answer would have been E. But this is actually one of the reasons why it's always a good idea to use conversion factors with more decimals so that it does not limit your final answer. Any questions so far? Okay. And feel free to stop me at any point if you do have a question.
I think I'm struggling with conversion factors. I'm struggling with it. I don't know
Yeah.
it.
Conversion factors is definitely one of those things that takes a little while to get used to. The most important thing to keep in mind when it comes to conversion factors is watch the units. Never put numbers until you have the units down. Whatever unit you start with, that has to go on the bottom so it cancels out. This unit and this unit, these diagonal units should nearly always match. So this pound cancels out with this pound.
Michael, can you drag this stuff? It's blocking the questions.
I'm sorry, I'm having a hard time hearing you. You're a little quiet.
This stuff you put here is blocking the questions. I can't see the questions anymore.
You mean this?
Yeah, thank you.
Yeah, no problem. All right. So, yeah, please feel free. Let me know if you need me to go over something a little bit more detail, or maybe throw up another question, or if you have questions of your own. Please feel free to bring those in at any time. We don't have to use the practice test. I'm just using it because it covers what most people are going to be covering. All right. Coins in a piggy bank are an example of what type of mixture? Oh, yes, absolutely. No problem. All right, yeah. Somebody asked me or requested that I send the conversion table as a file. I'm going to go ahead and do that right now. I have to tap into my Google Drive to do that, and that'll only take me a second. So let me pull up the table of conversions. Okay. Share.
7.
All right. And actually, yeah, I'll send it to you. Here we go. If you click on that, that will pull up that table of conversions. You may have to sign into a Google account to see it online, but even if you don't want to sign up for a Google account, if you don't have a Gmail account or whatever, you can simply download the file directly, even if you can't see it. You can always download the file directly, and that'll just put it on your computer, so that's fine too. Yeah, no problem. Okay, so, sorry. Yes, this is a heterogeneous mixture. Excellent. So, Linda, you're 100% correct. Coins in a piggy bank are a heterogeneous mixture. A heterogeneous mixture is anything where the parts can be distinguished. If the parts cannot be distinguished, it's a homogeneous mixture. Another name for a homogeneous mixture is a solution. So, this is a heterogeneous mixture. Homogeneous mixtures would be like salt water. Can't see the salt when it's dissolved in the water. Another homogeneous mixture would be like clear filtered apple juice. Can't see the different parts. Tomato juice would actually be a heterogeneous mixture. That's a common example they'll sometimes throw at you. But tomato juice would be a heterogeneous mixture because if you look at tomato juice, it actually has chunks and lumps in it.
Same thing with orange with pulp.
Yeah, orange with pulp would also be heterogeneous. Exactly. Absolutely. Very good. Now it says, which of the following is not an element?
Hello?
Hello.
Okay, it's working now. I'm so sorry to interrupt you. It's completely my bad.
Yeah, no problem. No problem at all. Yeah, and for 8 is a pretty easy question. Just look, what is not an element in the periodic table? And obviously the answer is water. Gold, carbon, tin, silver, they're all elements in the periodic table. Now, chemical change, it says, which of the following is a chemical change? And yeah, it's definitely A, burning sugar.
Ouch.
The question is, and this is a common mistake that if this is a common mistake that students make, phase changes are not chemical changes. So if you melt ice or if you boil water and it goes from a liquid to a gas, that is not a chemical change. Chemical changes tend to be difficult to reverse. So in other words, like for example, if you burn sugar, there's no way to make that go back to raw sugar, is there?
Also, another way to look at it,
Yep.
this helps me understand this question. You can also look at it as in, like, you know how ions decay? You can also look at it like when you're burning the sugar, you're just making it decay. You're not turning it into something else.
Well, actually, you are turning it into something else.
Oh.
No, I think when sugar melts, automatically it has changed from that being a rush, from being sugar.
I mean, so that's a really good point. It is possible to melt sugar without burning it. But the problem is the reason why you almost never see that happen is because in order to melt sugar without burning it, you have to in, have it in the absence of oxygen, no oxygen around. And unfortunately, that's just not going to happen. Furthermore, there are certain compounds that they will break down. They will break down into component parts before they ever reach a melting temperature. Like to get it up high enough to where it would melt, it'll just disintegrate first. So that's a possibility. But yeah, chemical change actually changes the whatness of it. You burn sugar, you turn it into carbon. And that's why it turns black. So, I mean, technically speaking, I mean, it depends. There's some different side reactions as well, but if you burn sugar, usually burning any sort of hydrocarbon, including sugar, sugar is actually a hydrocarbon with a lot of oxygen, you'll get carbon dioxide and water. But but thank you for bringing up that kind of point, because I want to hear your thoughts, because it's important to kind of bring those out, because a lot of times if you have a sort of misconception and you never express it, that misconception stays with you, and we want to kind of like free those. Yes.
So basically, it's a change of state, right?
A change of state would be like going from a solid to a liquid or a liquid to a gas.
Right. That's
That
a
would be like
difference.
melting gold. That's a physical change.
Okay.
That is physical. For a chemical change, you actually have to change what it is. The molecules themselves have to change.
Okay. Thank you.
So
So
a common example. Yeah, go ahead.
So what you're saying right now, because what I understand for chemical change is that it automatically changes from what it was to something else entirely. That's for chemical change.
Yeah,
So,
different molecules. I mean, the atoms are still the same. It's not a nuclear reaction. You're not changing lead into gold, but the atoms rearrange into different molecules. So, like instead of C6H12O6, which is sugar, or at least that's a simple sugar like glucose, you're going to change that into carbon dioxide and water. So these are completely different molecules. They're no longer the same molecules. They have different molecules with different properties. It's still composed of the same types of atoms, but they're just rearranged. And so that's a chemical change. So anything like burning anything is a chemical change. Burning, rotting, if anything rots, like leaves rot or decay, the decaying of the breakdown of different materials, digestion, cooking things oftentimes, in almost all cases, ends up in a chemical change. Like if you fry an egg, there's no way to make that go back to a raw egg. You've exerted a chemical change on that. And chemical changes tend to be very, very difficult to reverse. Whereas, for example, if you melt gold, all you have to do to make that gold solid again is just to cool it down, right?
Oh, got you.
So I don't know if that helps.
It does.
Good deal. All right, so let's go ahead and take a look at number 10. So which of the following is a property of a solid? Absolutely, the particles have fixed positions and they're very close together. Sorry, there's a little bit of a background noise from one of the people with the microphone on. I certainly don't mind if you have the microphone on while you're talking, but yeah, maybe we could just silence that just to avoid the background noise. Thank you so much. Sorry about that. Yeah, very close together. Very good. Which takes the shape of the container? That would be true of what?
Gas.
It would be true of a gas, but it would also be true of what?
Liquid.
Liquids.
Liquid.
And which one fills the volume of the container?
Gas.
Gas. That would be the gas. Yep. Very good. Now it says, so let's look at the temperature conversions. If the temperature has 20 degrees Celsius, what is the corresponding temperature on the Fahrenheit scale? Let's take a look at this. There's there's an equation that we can use between Celsius and Fahrenheit. There's actually two different ways to write this equation, but basically the equation is this. The degrees Fahrenheit is going to be equal to 9/5 or 1.8 times the degrees Celsius plus 32. 32 is the freezing point of Fahrenheit. So in this case, it says the temperature is 20 degrees Celsius. We want to solve for the Fahrenheit. Well, this is great because the equation's already set up to solve for Fahrenheit. All I have to do here is plug in the numbers, right? So I'll do 9/5, or like I said, you can also write that as 1.8 degrees Celsius. Now, in this case, the degrees Celsius I know is 20. And how many significant figures are in that number? How many significant figures are in that number?
1.
Actually, it's 2 because of the decimal point. It's 2 because of the decimal point. It looks like it would be 1, but trailing zeros are significant if there's a decimal point, so that's 2 sig figs. So now we can add to that the 32. Now, here's the thing. This 32 is,
Yes, I did. Thank you.
this 32 is, it would be considered kind of an exact number, a definitional number. So it would have unlimited significant figures. However, the number here limits your sig figs. So what's 9/5 times 20? 36. So yeah, 9/5 times 20 is 36. So this is going to be 36 plus 32. And that's going to give me a total of 68. So 20 degrees Celsius is 68 degrees Fahrenheit. Now, if you have a pretty good, this is also one of those questions where if you have a pretty good grasp of the difference between Fahrenheit and Celsius, you could actually probably answer this question without ever even looking at the rest of this. Because, I mean, me offhand, I know that 20 degrees Celsius is roughly about room temperature. So there's only one of these temperatures that's even close to room temperature, and that's the 68 degrees Fahrenheit. Now it says if the temperature is negative 55 degrees Fahrenheit, what is the corresponding temperature in the Kelvin scale? Okay, well this is a little bit more tricky. What we're going to have to do is we're going to have to take that equation that we just used, the degrees Fahrenheit is equal to 9/5 degrees Celsius. I'm sorry. 9/5 degrees Celsius plus 32, and I have to rearrange it to solve for Celsius. There's no way to go directly from Fahrenheit to Kelvin. So I'm actually going to have to solve for Celsius here.
That's just first here.
I'll first start by subtracting 32 from both sides. I'm going to change my color real quick. So minus 32 from both sides. And I don't know if any of y'all have noticed this, but when doing algebra and solving for a variable, you oftentimes will end up having to use reverse order of operations. So instead of going PEMDAS, you go like sad whatever, SADMEP. Basically, you go adding and subtracting. You undo the adding and subtracting first, and then you undo the multiplying and dividing. It's kind of interesting. But anyway, I'll subtract 32 from both sides. That gets the 9/5 degrees Celsius here. And this becomes degrees Fahrenheit minus 32. Now I just have to multiply both sides by the reciprocal of 9/5, so 5/9 on both sides, and that will just cancel out the other one. So that gives me the equation. Degrees Celsius is equal to 5/9 times, or rather 5/9, I actually have to multiply that times this whole thing, but 5/9 times the degrees Fahrenheit minus 32. All right, so let's go ahead and solve what's in the parentheses first. It's negative 55 minus 32. And so then let's see, here we go. Negative 55 minus 32, so that's basically going to be 5/9 times negative 87. And if I multiply that, what do I get? What's 5/9 times negative 87?
Okay, I'm a little confused where the 5/9 came in. I thought we were dealing with 9/5. So how did we come up with 5/9?
Ah, that came in because we needed to cancel. Okay, so we needed to cancel this 9/5, right? Because 9/5 degrees Celsius is equal to the Fahrenheit minus 32. In order to cancel the 9/5, I had to multiply by the reciprocal, which is 5/9.
Okay,
See, the 9 cancels out with the 9, the 5 cancels out with the 5.
gotcha. Okay, thank you.
Yeah, so that's where the 5/9 comes in. All right, so 5/9 degrees Fahrenheit minus 32. So now the equation for Kelvin is degrees Celsius plus 273. 273.15 if you want to get, like, super nerdy technical. Okay, now 5/9 times 87 is going to give us 5 divided by 9 times negative 87 is going to give us negative 48. Negative 48.3. 0.33, although admittedly it's only 2 sig figs. So what I'm going to do here then is I'm going to take that answer, I'm going to plug it in for the degrees Celsius. It'll be negative 48.33. Keeping in mind I only have 2 sig figs, only to the ones place. I'll add 273 to that, 273.15. And that's going to give me what? I'm seeing B. Yeah, it's going to be 224.8, which, since this is only the ones place, remember it's not how many sig figs you have. It's this is to the hundredths place. It's not how many sig figs you have. It's where the last significant figure is. You round your place to the one with the fewer decimal places, and so I'm going to have to round to the ones place here, and so this will end up being 225 Kelvin. And so that will in fact, Kelvin, that will in fact be B. So well done. Yes.
Yeah, another way I know how to do this thing is that first of all, when you want to calculate for Kelvin, you first of, like you said, you look for Celsius. Especially when they give you Fahrenheit, you look for Celsius first before you go to Kelvin.
Yes.
But if you're doing Fahrenheit, you do whatever number they give you in Celsius plus 32. No, times 1.8 plus 32. You put in those figures, you get your answer. Then also, if you're doing for Fahrenheit, no, for Celsius, when they give you a Fahrenheit number, whatever figure they gave you, you minus 32 from it, and you divide that value over 1.8. You give you a number.
Yeah.
And then work Celsius from there.
And you're not wrong. That's just another way of writing the same equation that derived through algebra. Degrees Fahrenheit minus 32 divided by 1.8. That's the same thing as multiplying by 5/9 times that. But yes, you're absolutely right. That's another way to do it. There's many ways to express the same equation, but ultimately speaking, you have to solve for the Celsius first, and then you use that one to get the Fahrenheit. Does that make sense?
Yes, please.
Awesome. All right. It says the phrase ability to do work is a oh, yes. Question?
No, no, sorry, I don't have a question.
Okay. No, please feel free to let me know if you want to skip ahead at any point. Yes, the phrase ability to do work is the definition of energy. Very good. A definition of energy. Thank you. Linda, you are 100% correct. So, energy is the ability to do work. And then 3.25 kcals is the same amount of energy as blank joules. This is just another conversion factor problem. And I'll go ahead and show it right here. But essentially, that there's two conversions that you need to know. And that is that well, kilo, of course, kcal is going to be equal to 1,000 small c calories, and also 1 calorie, small c calorie, is equal to 4.184 joules. So we'll have to use those both to be able to solve this. So essentially, 3.25 kcal is what we're going to start with. And the first thing we're going to do is convert kcals to cals. The unit on the bottom is kcal, because it has to cancel out with the kcal above. And then I'm going to convert that to calories. Now, K is a prefix, metric prefix kilo. Kilo means 1,000. So 1 kcal is 1,000 calories. Now this other one, I don't know if your professor will give it to you or not, or if you have to memorize it. Some professors make you memorize it. But the calories to joule conversion is the 1 calorie is equal to 4.184 joules. So if I multiply everything on top and I divide by everything on bottom, I end up getting 3 significant figures. Well, this is of course the 4.184 joules equal to 1 calorie. That is a 4 significant figures here. And this one, of course, the 1,000 calories to kcal is going to be a definition, so it's unlimited sig figs. But I'm starting with only 3. So I'm going to end up having only 3 significant figures in my answer. So it's going to end up giving me the 13,600 joules. Any questions on that? Okay, cool. Note, one should note that this is an interesting side fact. The kcal is actually the same as for the food calories that you see on your labels. Those aren't actually little c calories, those are kcals. All right. So let's go ahead and take a look at number 15. And by the way, if anybody wants to skip ahead to later problems, please feel free to let me know. That's totally fine. We can definitely jump ahead. All right, so 14 would be A, 13,600. All right, so let's go ahead and jump to 15. How many calories are required to raise the temperature of a 35-gram sample from 25 to 35 degrees Celsius? And this says iron has a specific heat. So this is another common equation in that particular chapter. You're going to have to use the equation Q is equal to MC delta T, or MCAT. Q is equal to MC delta T. So what you're going to go ahead and do is first we have to identify what we're looking for. Q is actually heat. We're looking for the calories, so that's what we're looking for. We're looking for the Q. The M is your mass. This is your M. 25 to 35. Okay, so delta T is always equal to final minus initial. So T final minus T initial. So what I would sometimes like to do here, and actually just so that doesn't get confused with a negative sign, I'm going to erase that. But what I sometimes like to do here is to list out my variables. So Q equals question mark. I don't know what that is. M is the 35.0 grams. The C is the specific heat. So that's the 0.108 calories per gram degrees Celsius. And then the delta T is going to be the final temperature, which is 35 degrees Celsius, minus the initial temperature, which is 25 degrees Celsius. Now, Q can be negative if the temperature drops. But we also have to kind of watch the wording of the question, because if it says how many calories are required to raise the temperature, you can't have a negative number of calories that are required, so to speak. You can have a negative change in heat, but you can't have a negative number of calories. So that's where a little bit of the semantics can sometimes trip you up. But there we go. We have 10 degrees Celsius as our change in T, or delta T. So now all I have to do at this point is plug in the information. Plug in my numbers. So 35 degrees Celsius. Oh, I kind of was lazy. 35.0. 0.108 calories per gram degree Celsius. Please forgive me. I put 35 degrees Celsius and I meant 35 grams. This is mass. It is not temperature. This is grams. So forgive me for that. And then the change in temperature is 10 degrees Celsius. Now, admittedly, this 10 really needs to have a dot here, because if I look at the sig figs here, this is the last significant figure in each of these numbers is to the ones place. So because of that, my answer should have significant figures all the way to the ones place. Since it's 10, I'm going to need to put a dot there. And that is going to be degrees Celsius. So then all I have to do now is multiply everything across. So that's basically going to be 35.0 times 10 times 0.108. And if I multiply that, that's going to give me 35 times 10 times 0.108. 37.8. However, because I only have two significant figures here, and these are each 3 sig figs, my answer is going to have to be rounded to 2 sig figs. Excuse me, and that's going to be 38. So, C. Now the cool thing for this is if you had something else that you were looking for, all you would have to do is simply solve for that variable. Let's say, for example, you were solving for specific heat. All you'd have to do is divide both sides by mass and change in temperature. Or if you're solving for mass, you just divide both sides by specific heat and change in temperature. So just do a little bit of algebra if you need to.
Can you repeat that, please?
Oh, I said, the cool thing about this is if it was asking you, for example, for another value, like if it was asking you to solve for the specific heat, you could just divide both sides of this equation by the mass and the change in temperature, that would get specific heat by itself. So whatever you have to solve for, you just get that variable by itself. Okay?
No, please, Michael, can you come back? I didn't understand. Why do you put here 3 SF 35 minus 25? Where do you take this one to add in, please?
Where do I get the change in temperature? 35 minus 25?
No, the SF, the significant figure, 10.
Ah, well that's, okay, so when you're, there's several different ways to show the significant figures here. Probably the easiest way is to show it vertically, so that's what I'm going to do. Effectively, you had 35 degrees Celsius, and you're subtracting 25 degrees Celsius, okay?
Mm-hmm.
The last significant figure in the first number is in the ones place. The last significant figure in the 25 is in the ones place.
Oh, yeah, yeah, yeah.
So when I subtract them, my answer has to be accurate. It
Oh,
has to
yeah.
have significant figures all the way to the ones place. So this has to be significant. The only way that I can make that a significant figure is if I put a little decimal point at the end.
Okay,
That or
yes.
if I want to write it as 1.0 times 10 to the first, but I don't really want to write it as 1.0 times 10 to the first because I don't like to use scientific notation unless I have to.
Okay, thank you.
Yeah, no problem. Now it says the specific heat of copper is 0.0920. This is number 16. 0.0920 calories per gram degree Celsius, and the specific heat of silver is 0.0562 calories per gram degree Celsius. So there's two different substances. So copper has this specific heat, silver has this specific heat. If 100 calories of heat is added to 1 gram of each metal, what is the expected result? So this is where understanding the formula can be helpful. So you have Q is equal to MC delta T. So I could actually calculate this if I wanted to, but I don't really have to calculate this. Okay? All I have to do is understand the relationship. Now, in each of these two cases, is the heat changing? Is the heat that's added changing? Yes or
Yes.
no?
Yes.
Nope, the heat's not changing. It's 100 calories of heat in each case. So I have a piece of metal, a piece of silver, and I have a piece of copper. Okay? And it's the same amount. It's a 1 gram of each. So it's 1 gram of silver and 1 gram of copper. And in each case, so the mass is the same. In each case, I'm adding 100 calories of heat. In each case, I'm adding 100 calories. So that's the heat is the same. So what's the expected result in terms of temperature? I'm really looking for the expected result in temperature. This is the piece that I'm looking for. So if I want to compare what happens to the temperature, what I can do to this formula is I can solve for temperature by dividing both sides by mass and specific heat. Okay? So that's going to give me the equation that delta T is equal to Q over mass times degrees Celsius. Does that make sense so far? Do you follow me?
Yeah.
Any questions over that?
Everything you're saying makes sense. It's just, I guess it's just hard for me to wrap around the whole, if 100 calories of heat is added, that means the temperature is not changing, but I'm sure it'll make sense at the end, so please continue.
Well, the temperature is changing. The temperature is changing, but we don't know what that temperature change is. the mass is the same and the heat is the same. The heat being added to each sample is the same, and the mass of the sample is the same in each case. The only thing different is the specific heat. So I could actually calculate this if I want to, but which
It'd be a
one?
bit much, yeah.
Yeah. So which one is going to end up having a greater change in temperature? If specific heat has or silver has a lower specific heat, right? If I put a lower number into the denominator, am I going to get a larger change in temperature or a smaller change in temperature?
Lower.
Actually, I'm going to get a larger change in temperature. If I divide by a smaller number, I'm going to end up getting a bigger change in temperature. You know, I think it might be helpful in this case to perhaps just go ahead and do the calculation. Just because this does seem a little bit confusing, so I'm just going to go ahead and do the calculation for y'all.
It is.
So let's say we put 100 calories on top here. And we have 1 gram of the metal on bottom. And this will be for silver. This will be 0.0562. And that's going to be calories per gram degrees Celsius. Or, yeah. Now what you're going to notice is that the calories is going to cancel out, and the grams is going to cancel out. I'm going to be left with degrees Celsius. So what do I get for that delta T for silver? Well, if I do it correctly, I should get, I mean, granted it's only one significant figure because this is 1 gram, but with not considering significant figures, because this is really a qualitative question, it's not a quantitative question, it's about 1779 degrees Celsius change that you get with silver. Now, if I did the same thing, but for copper, it's the same formula. The only difference is the 100 calories is still the same, and the mass is the same, 1 gram. The only difference is that I have a different specific heat. The specific heat of copper is 0.0920 calories per gram degree Celsius. Calories per gram degree Celsius. Yes.
I'm a little confused on how you know to use the 100 cal on top. Is that a specific formula that you're using to do that?
Yeah, well, I'm just using the Q is equal to MC delta T. And I just rearranged it to solve for change in temperature. See, this equation and this equation are the same equation. It's just I just divided both sides by mass and specific heat to get solve for delta T. And then it's just a matter of recognizing what each of these variables means. So you do have to know that the Q is actually going to be the heat energy, okay? And the heat energy is going to be given in calories or it's going to be given in joules. M is going to be equal to the mass. And specific heat is going to be, and now I use C, the book might actually use SH, but this is specific heat. When we say specific heat, what specific heat is actually short for is specific heat capacity. It's a heat capacity. In other words, it's the ability of a substance to hold heat. How much heat can a substance hold per degree Celsius? So this is specific heat capacity. Okay, so specific heat capacity, and this is change in temperature. Delta always means change. Delta is that little triangle. It's actually a Greek letter, but this is change in temperature.
So
Does that make sense?
the 100 cal that you put on the top comes from the number in the equation, right?
Yeah, it's basically here's my 100 calorie. This is your Q. Because
Okay.
it says if 100 calories is added to each to 1 gram of each metal, what
Yeah.
is the expected result?
Okay. Okay.
And so yeah, so I take 100 and then I just divide it by the mass and the specific heat. And if I divide it by the specific heat of copper and the 1 gram, I get only 1086. Well, actually, technically 1087 if I round to the nearest one, but technically speaking, it would only be 1 sig. But the point is, you can see that you're going to actually get a dramatically smaller temperature. And the reason is because you're dividing by a larger number. If you divide by a larger number, then your answer is going to be smaller. If you divide by a smaller number, your answer is going to be larger. That makes sense, right?
Yes, that makes sense to me because silver gets hotter, or it reaches a higher temperature because the number's smaller. The specific heat is smaller than copper itself.
Yeah.
Okay. Yeah. Okay. I understand the concept. That makes a lot more sense now.
So yeah, so basically the silver ends up reaching a higher temperature, so the answer is A.
Right.
So one of our members says they can't see the screen anymore. Ayabami, I recommend possibly logging out and logging back in. I think that'll fix the problem. Try leaving and coming back. I think that'll fix the problem for you.
Michael, could you remove the colored stuff so I could see the answer choices? I'm sorry.
Oh yes, absolutely. My apologies. And I'll also drag this over just a little bit. But
Yeah, I can't
yeah.
see anymore. Hold on. Thank you. Thank you. So,
Yeah. So basically, then the answer is going to just be the
A.
A. The silver reaches a higher temperature. And like I said, even though you don't have to do the calculation to answer this question, if you're not seeing it, go ahead and do the calculation. That's totally fine. You can definitely do that.
But is there any way we can just reason this thing out logically without actually going into all this drama?
Absolutely.
That's what I
Absolutely.
want to.
Yeah,
I like the
absolutely. 'Cause the idea, if you understand what specific heat, it's the ability of a substance to hold heat. So something with a higher specific heat is going to require more energy to increase the temperature because it's able to hold more heat for every degree Celsius. This is why, think of it like this. Have you ever like pulled something out of the oven? If let's say it's on aluminum foil, let's say it's maybe you had a pizza on aluminum foil or something like that, and you just picked up the aluminum foil with your bare hands right out of the oven, and you didn't get burned, right? If you haven't tried this, you can. I mean, it works. Aluminum foil, even if the aluminum foil in the oven is at 450 degrees Celsius or 450 degrees Fahrenheit rather.
Fahrenheit, yeah.
Yeah, so it's at broiling temperature. If you stick your hand in there and grab that aluminum foil and pull it out, you're not going to get burned. Why? Because aluminum has a ridiculously small specific heat. So if you and also because it's thin, and so it's not there's not a lot of weight there either. But aluminum has a very small specific heat, and so effectively it's not able to hold much heat for the temperature. So it will cool down by transferring all of its heat to your fingers. However, your fingers are composed of mostly water and also some other, tissue and flesh and things like that, but most of it's water. And water has a very high specific heat. So even if even if the aluminum drops its temperature dramatically by hundreds of degrees Fahrenheit, because water has so much higher of a specific heat, your fingers might only increase a few degrees, and you're not going to get burned by, even if like it's 105 degrees, you're not going to get burned. It's not going to cause serious lasting damage to your hand, or any sort of even temporary damage to your hand, just from that change in heat. And so things that have a low specific heat are things that heat up quickly and cool down quickly. It takes very little energy to spike them up, and it takes you can remove very little energy and it'll drop the temperature significantly. Things with high specific heat are things that take a very long time to heat up and a very long time to cool. Think of like water. Does that make sense?
It sure does.
Cool.
Must have just had. That's the truth.
It's kind of a fun topic. Like I wish I could teach this the way that I would love to teach this. I would bring stuff into class and we would, do all sorts of demonstrations and such and ask you questions. It'd be a lot of fun. But anyway, so let's take a look at number 17. Unless anybody wants to skip ahead, we'll just keep going. Jackson, you had a question? Sorry, I just noticed that.
No, you had already answered it for me. Thank you.
Oh, okay, no problem. All right, so 17 says on a heating curve, the plateau corresponds to what?
The question is, what is a plateau?
Oh, okay, plateau is like a flat part. So is it okay if I clear off all the drawings so far?
Yep.
Or all the writing? Is that all right if I scrap that?
Yes.
Okay. Oh, erase. Okay, here we go. So a heating curve looks like this, okay? And this is the degrees Celsius or the temperature, and this is heat added. And what happens is, let's say this is ice or something. It warms up until it reaches the freezing point, at which point the temperature stops going up. It just goes across. And then it increases again, at which point it reaches the boiling point, and then it flatlines for a while, and then it increases again. Well, here's the cool thing about this. What you have to understand is that when heat is added to the system, it can only do one of two things. It can either raise the temperature or it can change the phase. So let's say if this is water, this point here would be the freezing point of water.
Yeah.
So this is a solid down here, but this is melting here. So the temperature stays the same. The temperature stays the same, but the energy that's going into it is being used to break apart those attractions that are holding it together as a solid. Once those attractions are broken apart, you now have a liquid, and the liquid begins to warm up again. And then once the liquid has reached the boiling point, then once again the temperature stops. The temperature stops. So this is now boiling or evaporating. And then of course once you get up here it's a gas. So when it talks about the plateaus are these flat parts of the heating curve. Plateaus are like these flat parts of the heating curve. So this one is a plateau. This one is a plateau. So there's slopes and there's plateaus. So it says a plateau corresponds to what?
Change of state.
Change in state. Exactly. Cool. All right. Now it says so 18 is pretty straightforward. This is what elements are found in hydroxyapatite. That's a major compound in bones. That's just, reading, understanding the elements. That would just be which elements. What's the answer?
E.
Yeah. Calcium, phosphorus, oxygen, hydrogen. Very good. All right, now let's go ahead and skip to 19. It says the group 8A elements. The group 8A elements are blank. Which one of those is best answers that?
8A.
So 8A would be that last group on the far right.
You just explain that a little bit?
Sure.
They are non-metals, right?
So
They're
on the Yeah, on the
buttons.
periodic table, so I'm going to draw a little periodic table here. Okay. On the periodic table, you have this kind of shape, right? Well, in the periodic table, you have groups and you have periods. The groups numbers are on top. So you have 1, 2, and there's the A group elements and the B group elements, okay? I'm sorry, I can't draw a straight line to save my life, apparently. Okay, so here's your A group. So your A group elements are essentially sometimes also called representative elements. They refer to the last 6 rows in the first two, or last 6 columns in the first 2 columns. And they're numbered, this is 1A. I'm not going to draw the A's for all of them, but 1A, 2A, and then there's 3A, 4A, 5, 6A, 7A, 8A. So 8A is the last column on the periodic table, and we give that a special name. Does anybody know what those are called?
Noble gases.
Yeah,
Noble gases. And so what is true about noble gases? Which one of these is the best description of a noble gas? Probably not that they're liquids at room temperature, right?
I'm guessing they're not. I don't know. Who knows? Mixed with other stuff. That's my guess. I have no idea.
Yeah, they're noble gases because they are unreactive. They're unreactive. They want to be by themselves, like elitist. Think of it like noble, elitist. They don't want to mingle with the common folks, They're unreactive and they're rarely found in combination with other elements.
But
Now,
sorry,
yes, go ahead.
question. But so they're usually not found in other, like mixed with other elements, but they can be, correct? Like if you're a diver, they mix like weird gases together.
Oh, they will put helium in there with you, but the problem is it doesn't react with it. It's not found, when it says not found in combination, what it means is that it's not reacted with. In other words, it's always as an element. You'll only find it as an element. You won't find it mixed with other gases, or like chemically like bonded to other gases. And you're not wrong. There are rare cases. There are extreme cases where you might be able to get a noble gas to form a compound, but it is really, really difficult. And you have to use the most reactive element in the periodic table, which is fluorine. So while it's possible, it doesn't really happen too often, and it's really hard to make happen. So generally speaking, they're by themselves as elements.
Okay, sweet. Thank you.
Yeah, no problem. Good notion though. Thank you for bringing that up. That's a good question. And because the wording of this is not really clear when this is found in combination. You're right. I mean, it is in combination with other gases in terms of a diving tank, but that's not chemically combined. It's just mixture.
Okay.
Now, which of these would react vigorously with water? Does anybody know where the ones that would react vigorously with water is? So those would be the alkali metals. Alkali metals. Those are the ones that react vigorously with water. That would be these ones here.
Is that because the octet rule with the 7 valence electrons and the 1 from the alkalis typically, or?
Yeah. So in fact, they react explosively with water, and to say it reacts vigorously with water is an understatement. If you've ever seen a demonstration of sodium put in water, you actually, I mean, it'll literally explode. Actually, kind of funny story. In my high school, one of the students got a hold of, snuck into the stockroom and stole some sodium and threw it in one of the latrines, the toilets in the boys' bathroom, and flushed it. And of course, because it's so light, it floated and it got lodged up in there, and it exploded. It actually blew apart the toilet. It blasted off the stall door, and like embedded it in the opposite wall, like so. It was really bad. And in fact, that student actually went to prison for that. But um, don't mess with don't mess with sodium. It's a dangerous substance. Yes. Linda?
Yeah, I wanted to say that. Is it possible for you to just give us the characteristics of each of them?
Sure, absolutely. So 1A is the alkali metals. They are extremely reactive, explosively reactive. Um, and I'll go ahead and just label this alkali metals. Uh, oh, there we go. Alkali metals. There's also the next one that is important is 2A. These are the alkaline earth metals. And the alkaline earth metals, these are also reactive, but not quite as reactive as 1A. This would be like, for example, if you threw a chunk of calcium in water, it would fizz. I mean, calcium you don't think is a metal, but it actually is a metal. If you threw it in water, it would like fizz and bubble and produce heat, but it wouldn't like explode. So these are alkaline earth metals. Now, you don't have to know all of these groups, but the important ones are the alkali metals, the alkaline earth metals, and the halogens. The halogens are going to be these guys, group 7A. And these are also really, really very reactive, very dangerous. You can die from breathing in chlorine gas, but they tell you don't mix ammonia and bleach because it produces chlorine gas. And if you breathe that in, you will actually die. It will oxidize your lungs. So, um, halogens are very reactive in their elemental state. And in fact, the first scientists who tried to isolate halogens, actually, some of them did actually die because they breathed it in. Um, the British chemist Humphrey Davies actually lost half of his face to fluorine trying to isolate it. So like it's so reactive, it literally like ate away his face. Like half of his face got eaten off. He somehow managed to survive, but chemistry was a dangerous occupation in the 1800s. Especially since chemists at that time were like, let's taste this and see what it does. Let's see how it tastes like. And what will happen if we do this? And they didn't have the same sense of like uh, safety precautions that we do today, and there wasn't the same level of safety equipment as well. But it was because of their, sacrifice that we actually know so much about various things. But yeah, so halogens, alkaline earth metals, and then of course the noble gases, which is the last one we just talked about. Okay. And like I said, feel free to tell me if there's a particular question you want to go over, because we're probably going to have to stop soon. We've already gone like an hour and a half, and I apologize. I know we haven't gotten through that many, but if there's any you want to skip ahead to, we can definitely do that. For now, number 20, it says consider a neutral atom with 30 protons and 34 neutrons. The atomic number of this element is what? What's the atomic element? I think somebody actually already answered it. Yeah, A. So, A. So, basically, the atomic, oh, go away. Yeah. Atomic number is the same thing as the number of protons. These two are interchangeable. Yes, question. Yes, Ali?
If you're going to have to end it soon, is there any way after this one you can jump to problem 33 and move on from there?
Sure, absolutely. Let's do that. Nobody else has a problem with that? All right, we'll go ahead and skip ahead. Let's do 33, you said, right? All right, let's scroll down. 33, here we go.
Well, I'm kind of doing like 33 and onward.
Yeah,
really,
sure,
those
no
are the ones I have my biggest struggle in. So, if anything, I really want to try to get those before we have to end.
Sure, absolutely. That's no problem. I have no problem with that. All right, let's take a look. Now it says, which of the following gives the correct number of protons, neutrons, and electrons in a neutral atom of tin? So first of all, we have to understand that the symbol of an isotope there's a mass at the top, and then there's the atomic number, or the number of protons. The atomic number, remember, is the same thing as the number of protons on bottom. Okay? So in this case, how many protons does tin have? According to this isotope symbol.
50.
Yeah, 50. So it has 50 protons. Now, if it's a neutral atom, how many electrons is it going to have then?
50.
50 as well.
Exactly. Yeah, neutral atoms.
So 68.
Effectively, there's two quick, easy formulas that I can show you here. The charge is equal to the protons minus the electrons. If it's neutral, the charge is 0, so the protons have to be equal to the electrons. The charge is protons minus electrons. And then the other equation, or the other relationship, is the mass is equal to the protons plus neutrons. Protons and neutrons make up nearly all the mass of an atom. Now, electrons do have mass, but started writing the wrong thing. Electrons do have mass, but the mass is so small it doesn't really get included. Yes, question?
I always get confused on neutrons with the protons, because, like, you know, it's not just like an even down the middle that gets you the mass, because sometimes the neutrons are completely different numbers than the protons.
Absolutely.
But that's actually going to relate to my question that I have for you at the end of this lesson.
Yeah, basically the idea is this: neutrons are like the nuclear glue that hold the molecule together, that hold the nucleus together. Because keep in mind, protons are all positively charged, and what do you know about like charges? What do they do?
I am so sorry. I was
No, that's okay. Heather totally answered that correct. Absolutely, like charges repel. So how is it that these protons, these positively charged particles, are able to stay together in the nucleus? Well, it's something called a strong nuclear force. And what enables that strong nuclear force to keep those particles together is the neutrons, because the neutrons are basically the nuclear glue that holds the nucleus together. Now, for small atoms, you only need about an equal number of protons and neutrons. But for large atoms, you end up needing a lot more nuclear glue, a lot more neutrons to hold it together. So you'll see the number of neutrons increases significantly with the number of protons. So it increases at a faster rate. But that's just a little side note here. But yes, so we know that the mass of the tin is 118 because the top number is 118. And we know that the protons is 50. So then all you have to do to get the neutrons is what? Yep, just subtract them. And I'll just use N for the symbol for neutrons. Yeah, subtract 50 from both sides, and that gives you 68 neutrons. You get 68 neutrons. And so I have 50 protons, 68 neutrons, and 50 electrons. And since it wants it in that order, protons, neutrons, and electrons, 50, 68, 50, the answer is C. Does that make sense?
Yeah.
No? Did somebody say no?
No, I said yes, it does.
Okay. Okay, good.
I think, in my opinion, I think for us to be able to stick this down, first of all, is to know what atomic number is and to know what atomic mass is. Know what protons, neurons, and electrons are.
What?
Know that
Yeah.
protons and electrons are together. Who's that? Know that
Yeah.
protons and electrons are
I'm
together.
probably think of something to eat, honestly.
Yeah.
Like,
Oh, thank you. Thank you for coming, Brittany. We're glad to have you. I'm glad it was helpful.
More
Um,
Chinese.
So, let's go ahead and take the next one, 34. Electron arrangement of any particular atom shows blank. So electron arrangement is really like electron arrangement. Actually, you know what? I know the perfect thing to do. I'm actually going to upload a document here really quick. You know, if I end up going a little bit long, it's fine. I'm recording the session, so if anybody has to leave, they can always watch the end of this later. I want to upload another a periodic table here on the board because I think it'll be helpful. If I have it, I don't know. Let me check. Da, 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 da. All right. So, can you see my beautiful periodic table? Does it look as beautiful to
What
you as
she's
it does
giving
to
us
me?
to use in the exam.
Okay, cool. Yeah. So, does it look as beautiful to you as it does to me? No, just kidding. um, so basically, when doing electron arrangement, effectively all you're doing is saying how many electrons are in each energy level of the periodic table. So let me show you, for example, like how you would do electron arrangement, and that will help us answer this other question. Okay. So you can think of each box in the periodic table as a place for one electron, okay? As a home, shall we say, for one electron. Each box is a place for one electron. So, and then the energy levels are represented by the rows. This is the first energy level. This is second. Sodium, that's in the third energy level. This is the fourth energy level, etc. So, like say for example, I wanted to know what the electron arrangement for the element of carbon is, okay? Well, I have to fill up every box until I get to carbon. So in the first energy level, I have to fill up this box, and I have to fill up this box. So I fill up both of those, so that gives me a first number of 2. That gives me the number of electrons in the first energy level. For the second energy level, I have to fill up every box until I get to carbon. So I have to fill up this one, this one, this one, and this one. That 4 electrons, 4 boxes I have to fill up, so I need 4 electrons. So the electron arrangement for carbon is just 2, 4. Now, if it's for oxygen, I just have to fill up a couple more boxes, and I still fill up the same first row, still start at the beginning, but I'm going to actually fill it up to I get to oxygen, which is 6. So it'll be 2, 6. I have 2 electrons in the first energy level, and 6 electrons in the second energy level. Does that make sense? Okay. So, Tierney, you said that this is where you get confused. Can you elaborate on that? How can I help?
Good morning, Mr. Michael. Just can you start over and explain for me one more time, and then I can probably get it, grasp it.
Oh, sure. Yeah, so electron arrangement, you're just saying how many electrons are in each energy level. So, in each, looking at the different, so let's go over a few more examples. Let's say I'm doing aluminum.
Okay.
So aluminum is right here. So I have to fill up every box until I get to aluminum. So the first energy level, the first row is going to have how many electrons in it?
Oh, 1.
Well, I have to go all the way. I have to go all the way across too, right? So it'll be 1, 2, right? There's
Oh,
one
okay,
box.
okay.
Mhm. And then the
Okay.
second energy level has how many electrons I have to fill up? How many boxes do I have to fill up to get across the second energy level?
8.
Actually, it's going to be 1, 2, 3, 4, 5, 6, 7, 8. Remember, I have to go all the way to neon. I have to go all the
Okay.
way across to neon. And you see where that 8 comes from then?
Yes, sir.
Okay. Now the third energy level, I only fill up boxes. I only fill up boxes until I get to the element I'm looking for, in this case aluminum. So how many electrons do I have to fill up in the third energy level?
3.
3. So it's just going to be 2, 8, and 3. So
Oh.
that's what electron arrangement does. All it does is it shows you how many electrons are in each energy level of the atom. So if I was to draw a picture of this, let's say I had picture of the aluminum atom. So here's my nucleus here, okay?
Mhm.
I have the first energy level, the second energy level, and the third energy level, okay? And this is also what's referred to as a Bohr diagram, but in the first energy level, I had 2 electrons. I'll draw those 2. In the second energy level, I have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And in the third energy level, I have 3 electrons. So 1, 2, 3. So it's just showing you energy levels refer to how far you are from the nucleus. So it's just showing the electron arrangement just shows you how many electrons are in each energy level. Unfortunately, the periodic table is this really cool roadmap that shows you exactly how many electrons are going to be in each energy level because the energy levels are modeled by the rows.
Right. Okay. Thank you so much. I never even knew how to use it. Thank you so much.
Oh, good, good. I hope that helped.
Yes, it
Michael,
did.
could you just repeat a little, please?
I'm sorry. What did you ask, Linda?
Could you
My
just
apologies.
repeat? Could you just repeat this again? It didn't. It
Oh,
didn't
okay,
stay.
sure. So the periodic table is set up to mirror the energy levels. So each row in the periodic table represents an energy level. And so all electron arrangement does, and I'll actually type this out, electron arrangement, electron arrangement describes how many electrons are in each energy level. And rows in the periodic table match or can even be thought of as energy levels. And each box in the periodic table is a place you can think of as a place for 1 electron. So with aluminum, I fill 2 boxes in the first row, so then a 2. I fill 8 boxes in the second row, so that's 8. And then I'll only have to fill 3 in the third row because I only have to fill up boxes until I get to the element I'm looking for. And in the third row, I only need to get sodium, magnesium, and aluminum. And then I stop. So 2, 8, 3.
So,
And you should also, oh, go ahead.
so the valence shell is the outermost shell, right? So for aluminum,
Exactly.
in the valence shell, there's 3 electrons, correct?
And oxygen has 6 and carbon has 4. Exactly. The last energy level is the valence. The outermost energy level, the last energy level, tells you the number of valence electrons.
Okay.
Awesome. Way to bring that up. That's awesome. That is absolutely that's a good point. That's worth noting.
Nobody's ever showed me how to use the table. Like, this is like a whole new concept, which I think is crazy.
Same. Same with me.
Like, this is just
Well,
more helpful.
go ahead.
Ridiculous.
Oh yeah, no, most definitely. Like, I don't like the way a lot of this stuff is explained because a lot of times you don't see the connections, and
Yeah.
I know professors have to go through the material kind of fast, but I wish they would sometimes take the time to slow down and show the connection between the different things because there's a lot of things that you can do to help this make a lot more sense.
So, okay, I do have another question. So, like a hydrogen element or whatever, like a hydrogen atom,
Adam, yeah.
has the one. I guess does it technically have 2 valence shell or 2 shells, or is it 1? Sorry.
Oh no, it only has 1. So hydrogen. If I was to draw hydrogen's electron arrangement, it would literally just be 1.
Okay. Okay.
Yeah, because all I have to do is fill up this one and I'm done. And notice the total, if you add up these numbers in the electron arrangement,
Mm-hmm.
that should actually give you the same thing as the number above, the number the number of electrons predicted in a neutral atom, which is the same as the number of protons, right?
Ah, yeah.
So
Wow.
2 plus 4 is 6, and 2 plus 6 is 8. So this number should equal to what these add up to.
Okay. So the higher that you get in the amount of shells, are the bonds harder to break? Like I know hydrogen bonds are they weak?
They're weak.
Well, oh no, so it's interesting you mentioned that. What you call hydrogen bonds, I'm sure you heard that term in biology, right?
Yeah, yeah, yeah.
Um, hydrogen,
Stuff. Yeah.
so hydrogen bonds actually have nothing to do with actual chemical bonds of hydrogen. What we call hydrogen bonds are actually intermolecular forces, attraction between molecules, where whenever hydrogen happens to be bonded to a highly electronegative atom, like oxygen, oxygen, nitrogen, or fluorine, the the very polar nature of that bond causes the molecules that are made up like that to be attracted to one another very, very strongly. And that attraction is called hydrogen bonding. But it's not actually a bond. It's not actually a chemical bond. Although technically speaking, biology people will sometimes refer to them as bonds. They'll say it's the weakest bond.
Mhm.
But chemists, we have a little bit more of a different expectation for bonds. Um, we, we would say that that's simply an attraction, a force of attraction. It's not really a chemical bond. It's not a bond per se.
Okay.
So that actually doesn't have much to do with that. But um, the strength of bonds is a really complicated concept, and it's not something you really need to worry about yet here. What I will say is this. Yeah, you're opening a serious can of worms here.
It seems like everything we learned about chemistry and biology should be taken with a grain of salt, specifically anatomy and physiology.
Yeah, I mean it's tricky because I mean in some ways what they try to do in biology is they try to teach chemistry without actually teaching any chemistry. And I think that if that makes any sense, that they're basically, okay, so there's these
That sounds
reactions
very
and there's
true.
these molecules, but we're not going to actually explain anything. If you really wanted to understand the chemistry of biology, then going into biochemistry, it would be the thing to do. But that's a tough class, admittedly. Yes, question. There's somebody had a question, I thought.
Yeah, the way I kind of understood this one is that first of all, you start with a 2, right? But you're
Uh-huh.
following the atomic, is it mass number now? You're following the each number on each value on each element. So
Well,
you start with 2.
assuming, so you are assuming neutral atoms here, okay? You're assuming neutral atoms here. So, like for example, um, I'm assuming a neutral atom of aluminum in order to get the 283. If I was going to do, for example, if I was to do the aluminum 3 plus electron arrangement, aluminum 3 plus, well, aluminum 3 plus has already lost 3 electrons, hasn't it? And if aluminum 3 plus has lost 3 electrons, how many electrons does it have? Normally aluminum has 13. If it's a 3 plus ion, how many
10.
electrons? Yeah, it only has 10. It's lost 3 electrons so that it can be like the noble gas. And that's the whole point. It loses the electrons to be like the noble gas. So the electron arrangement for Al3 plus would just be a 2, 8. It would have the same electron arrangement as the noble gas. And that's what makes it so stable. That's why it wants to lose those 3 electrons, so it can have the same electron arrangement as the noble gas. So, like for example, with the oxygen, you'll notice that if oxygen wants to be like the closest noble gas, which is neon, it has to gain 2 electrons, and that would also turn it into a 2-8 electron arrangement. Does that make sense?
Yeah, that's going deep right now. Getting.
It's going a little deeper, but yeah. But basically, the idea is that yes, you start from the very beginning and you fill up every box until you get to the atom that you're looking for, and that you do that for any neutral atom. For any neutral atom, and admittedly, in almost all the cases that you're going to come across, you will be going after neutral atoms. Although I will say this: in the lab, it does actually ask you to go for a um, it does actually have you give the electron arrangements for charged atoms. So it does actually do that in the lab. So you will see that. But as far as the test go, I think you're going to be okay if you just know how to do the electron arrangements for this. Let's go back to the questions that we were looking at. Before I do that, do y'all feel like you have a pretty good understanding of how to get electron arrangement at this point? Okay, cool. So let's go ahead and then slide over back to the question. All right, so the electron arrangement of any particular atom, it shows the number of electrons in each energy level. So yeah, basically this is going to just be a C.
C? Oh, let's say that. C? Number of electrons in each level. Okay.
Yeah. So it's not really a diagram of the nucleus, because the nucleus doesn't have electrons in it. It's not the description of the shape of each electron. It doesn't have that. And it doesn't tell the number of isotopes, and it's not the maximum number of electrons. It just indicates the actual number of electrons in each energy level. Now, 35, let's see if you guys, I'm sure you can answer this one now. I have full confidence in you. What's the answer for 35?
Two-weighted one.
Which letter? Awesome, Carissa. 100%. Absolutely. Excellent. Excellent. Y'all got it. It's C. Very good. I'm so proud of y'all. All right. So 36 says the atomic size of atoms does what? Did you do periodic trends?
It increases.
Yeah. So I hate to say it, but B is actually not correct.
What the? Sorry.
You're like, what? A, you are correct. A.
Decreases going across. Okay, going across a period.
Yeah.
Decreases.
So it actually decreases, and I'll explain why. This has to do with, and this is why another reason why I'm not a fan of the way the 1406 course is is taught, and that's because it doesn't explain a lot of, it doesn't give you any of the background knowledge you need to know these things. It's counterintuitive. It does not make sense that the atomic size of atom would decrease going across the period. But okay, if the nucleus is the size of a basketball, then the atom, keep in mind, nucleus is the size of a basketball. The atom would actually be the size of Texas Stadium. So the electrons are flying around the nucleus in this huge, enormous cloud. The nucleus is the size of a basketball. The atom is the size of Texas Stadium. Okay? So most of the size of the atom is based on the electrons and how far away they are from the nucleus. Okay? So just because the mass increases going across the period, the actual size doesn't necessarily have to increase. And basically what it comes down to is this. The nucleus has a positive charge, right? So the nucleus has a positive charge, and it is attracting electrons to itself, okay? So it's attracting electrons to itself. I'm going to draw little arrows. It's pulling these electrons towards itself, okay? However, the inner shell electrons are shielding the outer shell electrons. So, for example, these guys in the second shell are protecting the outer ones from experiencing the effect of the nucleus. They're shielding it, okay? But I mean, and so effectively what happens is, but they offer no shielding to each other. And the shielding is not perfect. The shielding is not 100% perfect, but it shields it somewhat. Okay? But the outer electrons don't shield each other. So as you go across the periodic table, the number of protons keeps increasing. Okay? 17, 18. The number of protons keeps increasing. So that charge of the nucleus is getting bigger and bigger and bigger. And it's pulling these electrons in tighter and tighter and tighter. But even if I have more electrons in the valence shell, they're not doing anything to protect each other. So they're getting pulled in tighter and tighter as well. So it's only when you get a complete shell and you go to the next level that you end up getting an increase in size. So like, for example, if I was to describe the size of, like, go from like sodium. Okay. So I'm going to go ahead and clear this real quick. I'm going to actually clear everything. So sodium, let's say sodium is this big. Well, there's more protons, but there's still the same level of shielding. So all those electrons are getting pulled in tighter. Magnesium's only this big. Well, then aluminum's only this big. And silicon's only this big. The nucleus is getting bigger, but remember, the nucleus is only the size of a basketball. The Texas Stadium is getting smaller. So it just keeps getting smaller and smaller and smaller because there's more and more protons that are pulling them tighter and tighter and tighter into the nucleus, towards the nucleus. Does that kind of make sense?
Is it the atomic size that's the nucleus? Is it the atomic size, please?
Yeah, so atomic size, the size of the nucleus might be increasing, but it's the atomic size is decreasing because the nucleus is pulling those electrons in. So as you go across, however, once you go down, you add an entirely additional shell of electrons. So potassium has an entirely new shell of electrons, so it's bigger than sodium. But once again, calcium is going to start to shrink. It's going to be smaller. It'll be bigger than magnesium because it has an extra shell of electrons, but it's going to be smaller than potassium because the nucleus has an increase in charge, and so therefore it's going to start pulling them in tighter. Yes.
So would the answer be different if it said that that when you're going down, it's because you said if you're going across, it's going to be decreasing. But what if you're going down? Is it going to be
going down? It's increasing. Yeah, if you're going down, it's increasing because all you're doing going down is you are adding a completely additional shell of electrons. Well, and I mean you are adding more neutrons as well, but because there's a completely additional shell of electrons being added, it more than compensates for the fact that you also have the additional protons. So going down, yes, it definitely increases. Okay, cool. So let's drag this back over. Yes, question?
Yeah, quick question about the last question actually, about the electron arrangement. If it was C for 2881 since it was 19. However, on question 22, it asks what the maximum amount of the maximum number of electrons may occupy the third, and that's 18, is it not?
It is. Okay, so I'm really glad you brought that up. The maximum number of electrons that can occupy an energy level is equal to the energy level number squared, or 2 times the energy level's number squared. So the third energy level, n is 3, so 3 squared is 9 times 2 is 18.
Mm-hmm.
Well, how the heck is that right? I mean, why is it 18? We just saw those 2, 8, 8, whatever. Well, here's where that comes into place. And it doesn't look like, yeah, because remember we did label these 1, 2, 3. It only looks like there's 3 it only looks like there's 8 electrons in the third energy level, right?
Right.
Well, the problem is when you shift, I know this looks like the 4th energy level here, but for for reasons that are too complex to kind of go into, this it's sometimes referred to as the D block or the transition metals. Um, Effectively, these electrons are not just traveling in circular orbits, they actually have different patterns. And the pattern gets more complex, okay? Depending upon where you are in the periodic table. This is your S block, this is your P block, and the D block. So the S pattern is the simplest, the P pattern is a little bit more complex, but the D pattern is even more complex. It turns out there's kind of a trade-off. It requires a lot more energy to do the D pattern. I'll even show you what the patterns look like. S is just a simple spherical pattern. P kind of looks like a peanut. And the D looks like, I like to say it's a daisy, although I know it's not a daisy. We're going to call it a daisy. D pattern looks like that. Well, it turns out that the D pattern is so complex that it actually, it is in the third energy level. This is actually the third energy level. But it doesn't actually fill up until after the 4s. Because even though the fourth energy level is higher in energy, or even though the fourth energy level is further away from the nucleus and therefore higher energy, since it's a simple pattern, the 4s is actually lower in energy than the 3d. So there's a certain energy associated with being farther away from the nucleus, and there's a certain energy associated with the complexity of the orbital pattern, the pathway it follows. And it turns out that the combination of being in the third energy level and having this complex pattern is more energetic. It has a higher energy than the combination of being in the fourth energy level and having a simpler pattern. Now, you don't really need to know all of that, and that's what's really frustrating here. It tells you to memorize stupid things that are disconnected. Forgive me for saying that, I'm sorry. It's having you memorize disconnected facts without understanding the reason behind it. That's why I told you that the 2n squared rule, the number of electrons maximum number of electrons that can exist in an orbital is 2n squared. That's all it wants you to know. It doesn't want you to know anything about it. But then you're naturally left with questions like, well, why does the electron arrangement always show 288? Only looks like there should be 8 electrons in the third energy level. But that's why. Because once there's 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 here, so these there's 10 places for electrons. So if you add those 10 to the 8 above, you get 18. Does that answer your question?
Yeah, I mean, what you're saying makes sense. Of course, I don't get it because this is my first chemistry class in about 20 years. But it just seems, it seems like that's going to be a tricky one of just, I guess, knowing. But yeah, it's just tricky, I guess. But just one of those things you got to memorize for now, I suppose.
Yeah, unfortunately, chalk it up to one of those things that you memorize and never actually have to pay attention to ever again. But this is the maximum.
Except for on tests whenever I get it wrong.
Exactly. Maximum number of electrons is 2n squared. Maximum number of electrons that can be in any energy level, where n is the energy level. N is the energy level number.
Okay, thank you.
Yeah, no problem. I hope I didn't confuse people too bad.
No, the questions contradicting were confusing, and then this clears it up, but still, it's just one of those things, I guess.
Yeah. Okay. Well, I guess we'll go over 37 and 38, and then we'll probably call it a day. So it says, which of the following is the correct electron dot symbol for carbon? Oh, 21
I
real quick.
see. It's A.
Yeah. Okay. We can go. We'll hit 21 too. All right. Yes. See, it's A, and so essentially all you have to do with 37, all you have to do with these electron dot symbols is look for the number of valence electrons, and then put the valence electrons one at a time, one on each side before you double up. This is sometimes referred to as Hund's rule, although you don't need to know that term, Hund's rule. But basically, you put one electron on each side before you double up. Think of it like, you're going to a party, okay? And it's a pizza party. You can't take 5 pieces of pizza before everybody else gets one, right? That'd be rude. So you put one piece, each person gets one piece before you double up. And the same thing is true with Lewis dot structures. Each side gets one electron before you double up. So, and the number of valence electrons we already Heather kind of pointed out to us how we find that. That's basically from electron arrangement, right? You can just look over here and be like, oh, well, yeah, that's the number of valence electrons. Also, if you're looking at the top numbers here, you have 1A. Oh, I'm going to change that color so it's a little bit more readable, but 1A. The A number does actually tell you the number of valence electrons. So there's 1 valence electron in each of the first column, 2 valence electrons here. This is going to be a 3A for aluminum's column. So all of those elements will have 3 valence electrons. 4A for carbon's column, so all those will have 4. Nitrogen's going to be 5A, 6A. So that A number actually does tell you the number of valence electrons. So like, for example, if you were going to do oxygen, just to kind of give you another example here, oxygen has 6 valence electrons in 6A. So what you're going to go ahead and do is you can actually just write oxygen. I know it has 6 valence electrons. I'll do 1 on each side. 1, 2, 3, 4. But then now I can double up. 5, 6. So 1 on each side until each side has 1, and then the remaining 2 electrons to give me a total of 6. I'm going to double up. So it'll look like that. Does that make sense?
Yep.
Cool. Now, what about the metallic character of elements? Elements become more metallic, more metal-like as you go where?
It increases. D.
I'm sorry, I can't quite hear you.
Is it D? Increases going across a period, like we said just now?
Actually, that's not quite right.
Oh, again? Oh.
So if we look at the periodic table, let's take a look. And this is tricky because of the way it's worded, but there is a metal non-metal barrier, okay? And the metal non-metal barrier starts at aluminum here. So aluminum, and you do a little stair step down like that. So the metals are everything on this side of the periodic table, and the non-metals are everything on this side of the periodic table, the very small part, okay? A very small piece, okay? Very few non-metals. It's in the upper right side, and the metals are on the bottom left side, so that you can presume, based on the position of that metal non-metal barrier, that things are going to get more metallic as you go where? Down or up?
Across.
Well, things are going to get more metallic as you go down, right?
Down.
Because as you go down, it goes from non-metal to metal. So it's more metallic as you go down,
Okay.
and it's more metallic as you go where? To the left or to the right?
To the left.
To the left. So it's more metallic as you go down, and it's more metallic as you go to the left. Now, when it says across, it's usually referring to across to the right, but it really should say to the right instead of saying across. But anyway, so based on that, based on the fact that going down and to the left is going to give you a more metallic element, which one of those answers for 38 is the best answer? A, yeah, good job, Heather. It's A. Decreases going across. It wouldn't be C because C says it decreases going down, but we know that it increases. It becomes more metallic going down. Does that make sense?
Oh, this open is just so hard.
Okay. So, one last one as a favor to you, Heather, just because we love you. Let's go to 21. Now it says, the sample of chlorine has two naturally occurring isotopes. This isotope chlorine-35 makes up 75.8%, and chlorine-37 makes up 24.3%. Which of the following statements is true? So it's not actually asking you to calculate the average atomic mass, although you could. And actually, for this purposes, I think it actually would be helpful to show you how to calculate it. It's actually pretty simple. All you have to do to calculate the average atomic mass is do a weighted average. So a weighted average, I'll take the mass times the abundance. And I probably spelled abundance wrong. Yeah, I did. I think it's actually ENC. Anyway, so the mass is 35. Chlorine-35 has a mass of 35, right? And the abundance is 75.8%. Chlorine-37 has a mass of 37, and the abundance is 24.3%. So what I'm going to do here then is I am going to, okay, I don't want that. Okay. Okay, so what I'm going to do here is I'm going to multiply each of the masses by its corresponding abundance. And once I have the answer, I'll add them up. And then I will divide by the total abundance. Okay, so 35 times 75.8 gives me. Oh, by the way, interesting fact. This is actually how your professors calculate your grades when they say that your quizzes are worth 20% and your tests are worth, your quizzes are worth 10%, tests are worth 25%. This is how they do that. They multiply the percentage of its worth of a test is worth 25%. They take your test average, multiply by 25%, and then they take the quiz average and multiply that times 10%, and then they add them up and divide by the total percent to get your to get your average for your class. So 35 times 75.8 is 2,653. And 37 times 24.3 is 899. 1. So once I have multiplied the mass of each one by its appropriate abundance, and I add those together, that's going to give me 35.52. Or rather, 3,050. My bad. Let me fix that. There we go. 3,552.1. Okay. But now what I have to do is I have to divide by the total abundance. Okay. So I multiplied the mass times the appropriate abundance, but now I have to divide by the total abundance. Well, the total abundance is just going to be these two added together. Of course, that's going to add together to 100%, right? So I take my 35.52, or 35, I'm doing the calculation before I'm ready. 3,552 divided by 100%, and that's going to give me my average atomic mass. which is 35.52. So here's the thing. For which of the following statements is true? I cannot tell what the atomic mass will be. No, I can figure that out. I can figure out the average atomic mass. The average atomic mass, I've already figured it out. It's 35.52, so it's not 24.32. I know it's going to be an average, so it has to be between 35 and 37. And so C is the only one that makes sense. Yes.
Sweet. Thank you so much. I needed the explanation, and that made just way more sense.
Yeah, and the truth is, you don't even really need to calculate this because if the average atomic mass, and there's only two isotopes, the average atomic mass is going to have to be the mass somewhere in between those two masses, right? It can't be greater than 37. It can't be less than 35 because there's no single atom that has 35 or less than 35, and there's no single atom that has more than 37.
Aha. Okay. Yep. That makes sense.
Mm-hmm.
Sweet.
Cool. You're welcome. You're welcome. Well, this was fun. I'm glad I was able to help you guys, and I wish you the very best in your tests. Please feel free to come on by to the Science Learning Center tutoring room if you have any other questions. Oh, by the way, the full answer key was sent out to you in the email, and that answer key does have everything worked out. So if you need to look over that, plus there's additional practice tests as well. Actually, let me go ahead and include the link here to the practice test page so that if you want to practice with some of the other practice tests, you can. Each of them has its own answer key with completely worked out, so you can see exactly how the problems are worked out, and that'll give you like extra practice if you want to practice on your own.
Before you go, I had like 2 questions.
Okay, sure, no problem. Just copy and paste this into the chat. Here we go. Paste, bam.
Let me open that into my tab.
Yeah, no problem. Thank you. You're very sweet. I appreciate it.
I really appreciate you doing this. But my other big question was, so you work in the science lab. So if anything, like later in the days, would you consider if you have free time to if you'd be able to do another time where we could actually finish the exam practice?
Let's see.
Or just say, for example, maybe I could get on to the science thing later in the days.
Yes,
and see if
absolutely.
You're on, and we can just do it one-on-one.
Yeah, absolutely. Oh, thank you, Chris. You too. Absolutely. Anytime you want to, you can feel free to come into the SU Science Learning Center. If there's more than one of you, we can work. If that want to come do that, you can definitely do that. Just come into the SU Science Learning Center tutoring room. It's just like how you joined this one. It's just the first one on the page. And either myself or one of the other chemistry tutors will be able to help you out with any further questions you have on the practice exam.
What are your hours normally on the learning tutoring?
So my hours are 11 to 8 on Monday and Tuesday, 11 a.m. to 8 p.m. Monday and Tuesday. And my hours are 8 a.m. to 5 p.m. on Wednesday and Thursday. Fridays, I alternate back and forth between those two schedules. I'm always there between 11 and 5, but this Friday I'm actually working the night shift, so I'll be at 11 a.m. to 8 p.m. this Friday.
Oh wait, so today you'll still be on after right now?
Yes, I will be.
Oh, then I think just if you're I'm gonna go grab lunch. But after I eat lunch, maybe I can get a hold of
I might be grabbing lunch myself, so yeah, that's totally fine. But yeah, even if I'm not there, one of the other science tutors can definitely help me out.
I heard the last thing. I want to eat first.
Yeah, I mean the other chemistry tutor, Syed, he's pretty amazing. Like he has an encyclopedic knowledge of chemistry, and both him and I are really well trained with this. We can teach this without even needing a book. So.
Wow.
Okay. Well, I guess I'll try either or after I get back from eating lunch.
All right, sounds good. We'll see you then.
I have a second question.
So we're done this week. We're done this week, Micah. We're done this week with you.
Yes.
Ouch. Well, I may come in for the, but there's that I have statistics class at 1. So maybe after
Yeah,
that, I
you
might
can, no, it's up to you if you're done with me or not. I mean, you can certainly come
statistics
to the
class.
SE Science
Yeah.
Learning Center tutoring room. I'm still here today, the rest of today and tomorrow. But
Okay,
you're
that's
welcome.
fine. Let me finish my stuff. You're the best. Thank you. Thank you so much.
You're welcome. You're welcome.
Give me one more. I have one more really important question. I need to quick. Just give me like 30 seconds. Is that all right?
Yeah, no problem. Go ahead. Thank you,
Give me
Rose. I appreciate it. Thanks again, everybody, for coming. It was a lot of fun having you all here.
Okay, let me open up this.
Open it up, brother. Let's take a look.
Now let me share my screen. So my professor did some really weird stuff when he put this on here.
Okay.
Oh, I can't share.
Sure you can. I just have to make you into a moderator.
Power.
Oh, thank you, Tiana. Tierney, sorry. I'll make you a moderator. Don't worry. I have powers of which you know not.
This will be interesting.
Wait, never mind. I don't want to make you a moderator. I'm going to make you a participant. I'll give you secondary status. You can be a presenter. Okay, present. Present, my friend.
Head up for a moment. Okay. So I'm sharing my screen currently. So my professor had put this on, and this part right here got me really bad.
Yeah.
So on this one we were supposed to do the table and stuff.
Yes.
And most of these numbers confused me really bad. Like a great example is literally the second one, hydrogen.
Yeah.
He put 1 proton and then 1 neutron for hydrogen, but a mass number of 2. I was like, wait, hydrogen on my periodic table does not have a mass number of 2.
Yeah, but the reason is because you can't, for isotopes, you cannot rely upon the mass in the periodic table. The mass in the periodic table is the average of all the possible isotopes that exist, the weighted average. Deuterium does exist. Deuterium is like a heavy hydrogen. It has 1 proton and 1 neutron. However, its percentage is really, really tiny. It's like less than 1%. And of all hydrogen, less than 1% of all hydrogen is deuterium. So as a result, the mass of hydrogen, the average mass of hydrogen is about 1, because 99 point something percent of all the hydrogen in the world has a mass of only 1. But notice that the mass of hydrogen on the periodic table is not actually 1; it's 1.01, which means it's a little bit more than 1, and that's because there is such a thing as deuterium, and there is such a thing as tritium, whereas 2 neutrons and 1 proton, and has a mass of 3. So you can never use the mass number from the periodic table. You can never trust the mass number from the periodic table. You have to add the protons and the neutrons together to get the mass.
Okay.
Well, the periodic table just gives you the average. It doesn't give you,
I'm gonna look into this a little bit. I may need help understanding this a bit better. But besides from that, that was my first question. I was really confused, but it seemed I get what you're saying now. I just completely approached it the wrong way.
Yeah. Like, for example, interestingly enough, if you look at the molar mass of bromine, the molar mass of bromine, it's like about 80, but there is no isotope of bromine that has a mass of 80. There's 2 isotopes of bromine that commonly exist, and that is bromine 79 and bromine 81. So about half of the atoms have a mass of 79, and half the atoms have a mass of 81. But the average atomic mass in the periodic table is 80.
Okay.
So, unfortunately, there's so like I said, that average atomic mass doesn't tell you the mass of any specific isotope, or even necessarily the mass of any isotope. It just tells you the average of the masses.
All right. Well, thank you so much for the explanation.
Yeah, no problem.
I am going to, I think what I'm probably going to do is I'm going to go get some lunch. I'm going to go watch his second class review on Lab 6 and try to do Lab 6. And then somewhere between that and 5, I'm probably going to jump on here again and see if you or the other professor is available for tutoring.
Okay, sounds
And see if I
good.
can do a practice exam with y'all. Because I will admit, we're doing the practice exam, and there's stuff on here that I haven't gone over yet in my class, like the temperature part.
Oh yeah, well, and you might not have gone over it, depending upon the professor. They might not have actually covered that. So, that's why I said you really do want to make sure that you want to focus on those areas that your professor has actually covered and will actually have on the test, because different professors cover things in a different order. The most complete, here, let me show you something really quick. Um, I'm just going to share my screen with y'all. The most complete practice exam that I have is the one that I made myself on the bottom. And this has pretty much everything, I think. Okay, maybe not. Okay, matter and energy. We do cover matter and energy here, but this one here has 100 questions on it. Obviously, you may not want to do all 100 questions, but it's organized by topic, matter and measurement. There's a bunch of questions over that. Conversion
Okay.
factors and all sorts of stuff. And then there's density and related calculations. There's about uh, uh, some questions there. There's atoms and elements. That's where we talk about the different types of trends in the periodic table and the isotopes and all that good stuff and charges. And then there's electron arrangement, um, compounds and their bonds. So some of you are going to have some discussion about ionic versus covalent bonds and naming and writing of formulas and things like that. Some of you have already done that. So that there's lots of questions like that over here. So this practice test has a lot of different questions. So like I said, what I would recommend is just take a combination approach. This one covers everything except the matter and energy. If you want to jump into the next one, the sections are labeled. The practice test 2, the sections are labeled. If you want to go skip to where it says the matter and energy section, which starts, I think, at question like 40. Yeah, here it is, matter and energy. Here's all the questions over specific heat and physical, chemical change, etc. So, and there's a good 30 questions over that. So, if you really want a lot of practice, this second test over that has basically questions 40 through 70. The second test questions 40 through 70, and the first test, basically the whole thing, which has 100 questions. Obviously, you don't have to do them all, but those two practice tests will cover everything that you could potentially need. Now, the question is, if it's not something if it's not something your professor covered, then you don't have to cover it, or like you don't have to focus on it. You can skip that part. If your professor did not cover any matter and energy thing with like temperature, specific heat, just skip that part. If your professor did not cover naming and ionic and covalent compounds and things like that, then just don't worry about that part. Because like I said, unfortunately, the different professors are kind of covering the chapters in different orders, which is not super great, but it is what it is.
All right. Well, thank you so much. I really appreciate the help.
Yeah, no problem.
But yeah, I'm gonna get going. You stay safe.
All
Thank
right,
you
you
so much,
too.
sir.
Take care, y'all. Bye-bye.
Bye.